Imagine you are walking towards a specific point on a map. You get closer and closer. You might take big steps at first, then smaller steps as you near your destination. A limit in mathematics is a very similar idea. It describes what happens to a function, which is like a mathematical rule, as its input gets nearer and nearer to a particular value. We are interested in the output value the function is heading towards. This concept is fundamental to understanding change in mathematics. It helps us predict behavior with incredible precision. So what is a limit formally but simply put? Think of a function, let's call it f(x). This function takes an input, x, and gives an output. A limit tells us about the value that fx approaches as x itself approaches some specific number, let's call it ce. We are not necessarily asking what fx at c, instead we are curious about the trend. What value is fx homing in on as x gets incredibly infinitesimally close to c from either side? This destination value is called the limit. It is very important to understand this key distinction. The function does not actually have to reach the limit value at that specific input point. Sometimes a function might be undefined at c. For example, we might have a fraction where the denominator becomes 0 at c. Yet, the function can still have a limit as x approaches c. It is all about the journey, the tendency, the value being approached as we get tantalizingly close. The limit describes this ultimate destination, even if the destination itself has a do not enter sign. Think of it like trying to touch a very specific spot on a wall in a pitch-black room. You reach out your hand, you move slowly, getting closer and closer. You can sense the wall. You can tell exactly where that spot is. You know this, even if, for some reason, you are told you can never actually make contact with that precise spot. The limit is that precise location your hand is undeniably heading towards. It's the value everything points to, the inevitable conclusion of the approach. The idea of getting close in mathematics needs a little unpacking. It's not just about being nearby, it's about being able to get close. This means we can make the distance between our input x and the target value c as small as we want. Imagine you are trying to measure a tiny object. You might use a ruler, then a magnifying glass, then a microscope. Each tool lets you get a more precise, closer look. Limits work on a similar principle of refining our proximity. When mathematicians say infinitely close, they mean a distance smaller than any positive number you can name. If you say 1/trillionth, we can get closer. If you say 1 googolth, we can still get closer. This is not a physical closeness you can achieve by walking. It is a conceptual closeness, a theoretical journey towards a point. It is this power to get unimaginably, yet precisely close that gives limits their strength in defining complex mathematical ideas. We are exploring the immediate neighborhood of a point with an infinitely powerful zoom lens. We use special notation to talk about this. When we say xc, it reads as x approaches c. This little arrow is packed with meaning. It signifies that x is taking on values that are successively nearer to c. It can approach from values less than c, from the left side on a number line. Or, it can approach from values greater than c, from the right side. For the overall limit to exist, the function must be heading towards the same output value, regardless of the direction of approach. Let's use a number line to visualize this. Suppose we want to see what happens as x gets close to the number 3, we could pick numbers like 2.9, then 2.99, then 2.999, getting closer from the left. Or we could pick 3.1, then 3.01, then 3.001, getting closer from the right. We then look at what the function fx is doing for these input values. Is the output fx steadily approaching a consistent number? If so, that number is our limit. You might be surprised to learn that the concept of limits isn't just confined to dusty math textbooks. We encounter limit-like ideas in everyday situations quite often. Consider baking a cake. There's a point where the cake transitions from being batter to being perfectly baked. You check it with a toothpick. As the baking time progresses, the state of the cake approaches doneness. The limit is that ideal state where the toothpick comes out clean. You get closer and closer to this state over the cooking duration. Another simple example is filling a glass with water. As you pour, the water level rises. It gets closer and closer to the brim of the glass. The maximum capacity of the glass is the limit. You can pour water until it is almost full, then a little more until it is even closer to full. The volume of water approaches the total volume the glass can hold. You might stop just short to avoid spilling, but you understand the concept of it being full. That's the limit. Think about a car approaching a red traffic light or a stop sign. The driver applies the brakes. The speed of the car decreases. It goes from, say, 30 miles per hour to 20, then 10, then 5, and eventually its speed approaches 0 as it reaches the stop line. The limit of the car's speed as time approaches the moment of stopping is 0 miles per hour. The car gets infinitely close to having no speed at that precise point of full stop. This gradual reduction is a real-world manifestation of approaching a limiting value. Even in technology we see this. Imagine zooming in on a digital photograph. As you magnify the image, you see more detail, up to a point. Eventually you zoom in so much that the image starts to look blocky. You see the individual pixels. You have reached the limit of the image's resolution. The clarity approaches a certain maximum, and then further attempts to zoom don't yield more true detail, but rather expose the building blocks. This boundary of useful magnification is like a limit. The concept of limits, so crucial to modern mathematics, wasn't just dreamed up overnight by a single person. It was a gradual evolution, with many brilliant minds contributing pieces to the puzzle over centuries. Ancient Greek mathematicians like Archimedes used methods that hinted at limit concepts when calculating areas and volumes of complex shapes. They used a technique called the method of exhaustion, which involved approximating a shape with polygons of more and more sides. This was an early form of approaching a true value. The real groundwork for limits as we understand them in calculus was laid in the 17th century. Sir Isaac Newton, working in England, developed his method of fluxions to understand rates of change like velocity and acceleration. Fluxions were essentially derivatives, and his fluents were integrals. While he didn't use the formal epsilon-delta definition of limits we use today, his reasoning heavily relied on the intuitive idea of quantities getting indefinitely or ultimately close to each other. His work on physics and motion demanded this new way of thinking. At around the same time, but working independently in Germany, Gottfried Wilhelm Leibniz was also developing calculus. He introduced notation like dx and dy to represent infinitesimally small changes in x and y. These infinitesimals were thought of as quantities smaller than any real number but not zero. While the concept of infinitesimals faced some philosophical criticism for lacking rigor at the time, it was incredibly powerful for calculation and discovery. Leibniz's approach, like Newton's, captured the essence of looking at behavior at an infinitely small scale. It was not until the 19th century that the concept of a limit was put on a truly rigorous footing. Mathematicians like Augustin Louis Cauchy and later Karl Weierstrass developed the formal epsilon-delta definition. This definition removed the vagueness of infinitely small or approaching. It provided a precise logical way to define what it means for a function to approach a limit. This formalization was a critical step in making calculus mathematically sound, and paved the way for further advancements in analysis. Section 5. The bedrock of change, why limits matter in calculus. Calculus, the mathematics of continuous change, simply would not exist without the concept of limits. Limits are the fundamental building blocks upon which the entire edifice of calculus is constructed. If calculus is a powerful engine that drives much of science and engineering, then limits are the precision-engineered components that make that engine run smoothly and accurately. Understanding limits is the first crucial step to unlocking the power of calculus. They are not just a preliminary topic, they are the very soul of the subject. One of the two main branches of calculus is differential calculus. This deals with rates of change. How fast is something changing at a specific instant? To answer this, we use a concept called the derivative. The derivative of a function at a point tells us the slope of the tangent line to the graph of the function at that point. And how is this derivative defined? It is defined as a limit. Specifically, it's the limit of the slope of secant lines as the 2 points defining the secant line get infinitely close to each other. The other major branch is integral calculus. This is concerned with accumulation, such as finding the area under a curve or the total distance traveled given a varying velocity. The tool for this is the integral. An integral is also defined using limits. We approximate the area under a curve by dividing it into many thin rectangles and summing their areas. The exact area is then found by taking the limit of this sum as the width of the rectangles approaches 0 and their number approaches infinity. This is known as a Riemann sum. Without limits, defining instantaneous velocity would be a paradox. How can something be moving at an instant, which has no duration? Limits allow us to consider the average velocity over an infinitesimally small time interval. Similarly, finding the exact area of a shape with curved boundaries was an ancient problem. Limits provide the rigorous framework to sum an infinite number of infinitely thin strips to get that exact area. From physics to economics, the applications stemming from these limit-defined concepts are vast and transformative. Section 6. Spot the difference limits versus other math ideas. It is useful to compare limits to other mathematical concepts to truly grasp their unique role. One common point of confusion is the difference between a limit and simple function evaluation. When we evaluate fc, we are finding the exact output of the function at the input c. The limit of fx as x approaches c, however, tells us what value fx is heading towards near c. The function might not even be defined at c, or its value at c could be different from its limit there. Limits are also distinct from approximations, though they are related. An approximation is a value that is close to the true value but not necessarily exactly it. For example, we might approximate pi as 3.14. Limits, however, are about the concept of getting arbitrarily close. It's not just close enough for practical purposes, it's a theoretical construct that says we can get closer than any specified tolerance. The limit is the exact value being approached, not just a good guess. This precision is what makes limits so powerful in formal mathematics. Consider sequences, which are ordered lists of numbers. We can talk about the limit of a sequence. This is the value that the terms of the sequence get closer and closer to as we go further and further out in the list, as the term number approaches infinity. For example, the sequence 1/2, 1/4, 1/8, 1/16 has a limit of 0. Each term gets progressively closer to 0. This is a specific application of the limit concept focusing on discrete inputs, the term number rather than a continuous variable approaching a point. Finally, limits are intrinsically linked to the idea of continuity. A function is said to be continuous at a point c if three conditions are met. First, the function must be defined at c fc must exist. Second, the limit of the function as x approaches ce must exist. Third, and most importantly, the limit value must be equal to the function's value at ce, lim x approaches cfx equals fc. So limits are essential for defining and understanding what it means for a function to have a smooth, unbroken graph. Section 7. When limits don't behave, understanding non-existence. While the idea of a function smoothly approaching a specific value is common, it's important to know that limits do not always exist. Sometimes a function's behavior as its input approaches a certain point is more complicated. It might not settle down towards a single, well-defined number. Recognizing these situations is just as crucial as finding limits when they do exist, as it tells us about important features or problems with the function at that point. These are the rebels of the function world. One way a limit might fail to exist is if the function oscillates too wildly as it nears the point. A classic example is the function fx equals sin 1x as x approaches 0. As x gets closer to 0, 1x becomes very large, either positive or negative. The sin e function then oscillates faster and faster between -1 and 1. It never settles down to approach a single value. No matter how closely you zoom in near x equals 0, the function continues its frantic dance, never committing to a specific output. Another scenario where a limit doesn't exist is when there's a jump in the graph of the function. This often happens with piecewise defined functions. Imagine a function that equals x for x less than 1, but equals x plus 2 for x greater than or equal to 1. As x approaches 1 from the left side, values less than 1, for x approaches 1. But as x approaches 1 from the right side, values greater than or equal to 1, fx approaches 1 plus 2 equals 3. Since the function heads towards different values from the left and right, the overall limit at x equals 1 does not exist. Sometimes a function might grow without bound as x approaches a certain point. For instance, consider fx equals 1 over x squared as x approaches 0. As x gets closer to 0 from either positive or negative side, x squared gets very small and positive. Therefore, 1 over x squared becomes an increasingly large positive number. We say the limit is infinity, but technically this means the limit as a finite number does not exist. The function is going to infinity, not settling near a specific value. Understanding these cases of non-existence is key to analyzing function behavior. Section 8. Beyond the blackboard. Limits shaping our world. The concept of limits, though born from abstract mathematical inquiry, has far-reaching consequences and applications in the real world. It's not just for mathematicians to ponder. It underpins many technologies and scientific understandings we rely on daily. In engineering, for example, limits are crucial for designing safe and reliable structures. Engineers need to understand the stress limits of materials. They use calculus, built on limits, to calculate how structures will behave under various loads, ensuring they don't approach a breaking point. In the field of economics, limits are fundamental to concepts in marginal analysis. For instance, marginal cost is the change in total cost from producing one additional unit. This is essentially a derivative, which is defined by a limit. Businesses use these ideas to determine optimal production levels and pricing strategies. How much more will it cost to make one more item? How much more revenue will it bring? These at-the-margin questions are answered using calculus, and therefore indirectly, using the idea of approaching a certain point. Physics is another domain deeply intertwined with limits. The very definitions of instantaneous velocity and acceleration, which describe how an object's motion changes at any given moment, are limits. Think about calculating the trajectory of a rocket or the path of a planet. These calculations rely on differential equations which are built upon derivatives. Concepts like terminal velocity, the constant speed a freely falling object eventually reaches when air resistance balances gravity, also involve limit-like behavior as forces approach equilibrium. Even in computer science and technology, limits play a role. When analyzing the efficiency of algorithms, how quickly they run as input size grows, computer scientists often use Big O notation. This notation describes the limiting behavior of a function. In computer graphics, smooth curves and surfaces are often generated using mathematical functions and their derivatives, ensuring that visual representations appear realistic. From the code that runs our apps to the design of complex systems, the principles derived from limits are subtly at work. Section 9. The Never-Ending Journey. The Power of Infinite Closeness. To sum up our exploration, the concept of a limit in mathematics is all about understanding the behavior of a function by examining what happens as its input gets infinitely close to a particular value. It's a journey of approach, a meticulous investigation of the neighborhood around a point. This seemingly simple notion of getting closer and closer is remarkably powerful. It allows us to handle situations where direct evaluation is impossible or uninformative, giving us a window into the very essence of functional behavior. We have seen that limits are not just an isolated topic, but the absolute cornerstone of calculus. They provide the rigorous definitions for derivatives, which measure instantaneous rates of change, and integrals, which measure accumulation. Without limits, the entire framework for understanding change, motion, growth, and areas of complex shapes would crumble. They are the intellectual toolkit that allowed mathematics to move from static calculations to the dynamic study of how things vary and evolve continuously. The journey of developing the limit concept itself, from the intuitive ideas of Newton and Leibniz to the formal epsilon-delta definitions of Cauchy and Weierstrass, highlights the progress of mathematical thought. It shows how a need to solve real-world problems like those in physics spurred the creation of new mathematical tools, which then required further refinement to ensure their logical soundness. This evolution underscores the dynamic interplay between application and abstraction in mathematics, a field constantly striving for greater clarity and precision. Ultimately, mastering limits opens up a vast landscape of mathematical understanding. It is the key that unlocks calculus, and through it, a deeper appreciation of the principles governing the natural world and the engineered systems around us. From the smallest subatomic particles to the grandest cosmic structures, from economic models to the algorithms in our pockets, the ripples of this powerful idea of infinite closeness are felt everywhere. It is a testament to how a focused look at the almost there can reveal so much about what is.